Good morning. Good. Okay, let's carry on with the integration here. Today we're going to look at 15.4. And we're going to explore double integrals in polar coordinates. In case you've forgotten what polar coordinates are, let's do a very quick review of that. We're used to seeing things in what's called the Cartesian or the rectangular coordinates, x and y. Right, so we're used to specifying the x and y of a point, and that's how we locate things in the Cartesian coordinate. So the point 3, 2 means 3 units in x and 2 units in y, right? That's how we locate stuff. But that's, of course, not the only way to locate something. You've seen the polar coordinate. In polar coordinates, to locate a point, we give a distance r from the origin and the angle theta measured from the positive x-axis. Okay, so for example, the point in polar coordinates, the point 2, comma, pi over 3, means first we locate the angle pi over 3, which is over here. Then we put a point down that's 2 units away from the origin. Here's the origin. Let's say that's 1, and this is 2. So right here, let's call that distance 2. Okay? So if you took 162 or 166, you remember seeing this. If you haven't seen this before, well, it's a very simple thing. It's just a different way to locate a point. The conversion. This is very important for what we're about to do. We know the usual Pythagorean identity. Distance squared is x squared plus y squared. So given something in the rectangular / Cartesian coordinate, we can use this to find r. And we also know the relationship between x and y and r and theta. Okay, so this is a very important thing that's going to help us integrate stuff in polar coordinates. Okay, now let's look at what happens when we do a double integral. First, let's revisit the Cartesian just a little bit more. This dA in the Cartesian coordinate the differential element here is a rectangle. So you imagine this is the stuff you're integrating over. And dA is just some little tiny rectangle inside here. If you blow it up, right? Just some tiny rectangle whose width is dx, whose height is dy. So dA, the differential element, is dx dy. It is also equal to dy dx. In polar, that's a slightly different story. It's a little bit more complicated. All right, so you can see what's going to happen here. Let's consider a region D is equal to r comma theta, such that theta is between alpha and beta, whatever alpha and beta are, and r is between A and B. Just two constants. So we're going to bound theta by constants. We're going to bound r by constant, just for a very, very simple region, so we can come up with a formula for dA. That's the second key that we need to have before we can do any integration in there, in that coordinates. Okay? So let's, for simplicity, let's assume that this region is in the first quadrant. So let's say this is alpha, this is beta, and let's say the A and B are just, so this is A, and we'll make B just slightly bigger. So from here to here, let's call that B. All right? So you can see that in general, that little segment of a little area bounded by constants in polar coordinates is kind of a chopped off, like a slice of pizza kind of shape, right? You take a slice off and then someone cuts half of it off and you get this, it's like the crust on the pizza, right? The crust on the slice of pizza. That's the thing we're dealing with. That's not a rectangle. So we have a little bit of problem here with finding dA, the expression for dA. In Cartesian, it's dx dy, very simple. Here, we got a little bit more going on. Okay, so let's shrink well, actually, let me take that little wedge shape, the pizza crust shape again, from the last page. Right, this little segment here, this is delta R. And from here to here, that's the outer radius. From here to here, this is the inner radius. I'll call that R in and R out. And the difference in the angles, that's delta theta. And now we're going to use the usual calculus trick here. We're going to imagine we're shrinking delta R and delta theta to something very, very, very small, so that eventually delta R turns into dr, and delta theta turns into d theta. And these are differential elements in R and in the angle theta. when we shrink delta r and delta theta to something very tiny, what's going to happen is that r out will be roughly equal to r in. And we're going to call that thing r just for simplicity. The inner and outer radius will become so small that they're essentially the same thing. So our pizza crust shape, when you shrink delta r and delta theta to something very, very small, this will become almost like a rectangle. Right? If you keep shrinking this thing here, the two curved segments here will be roughly straight. So it's almost like a rectangle. And you remember how to find a curved part of a circumference? The circular segment, I guess that's what it's called. If you don't remember, you need to find the radius times the angle in between, the included angle and the radius to that point. So that's what the outer segment will be. Now when we shrink these things, r out and r in is roughly equal to the same thing, r. So this thing right here will become r times d theta. And then this delta r here becomes dr. Okay? And the important thing here is that this is almost a rectangle. And the smaller we can make d theta and dr, which is what we're going to do anyway, the closer it is to a rectangle. So what that's going to tell us is that the dA, the small differential element, is roughly a rectangle whose area is r d theta times dr. Right? It's a rectangle with dr and a height r d theta. And usually we write it as r dr d theta. And this is the key. You got to remember the differential element in polar coordinates is r dr d theta, whereas the differential element in rectangulars dx dy or dy dx. And therefore, the original one can be turned into the same function, but x becomes r cosine theta, and y becomes r sine theta, and dA becomes r dr d theta. And once again, this is just the function f of x, y expressed in polar. And this is our dA in polar. Okay, so that's what we need to do. Okay, let's try this on an example. Suppose we're asked to compute this double integral. Double integral over the region R, cosine x squared plus y squared is equal times dA. And the region R is a region in quadrant 2 between circles with center at the origin and between circle radius 1 and a circle radius 4. Okay, the very typical setup, we're integrating the function cosine of x squared plus y squared. Again, imagine this is the height of the surface above the region. We're finding a volume below that surface over this little segment, a little circular segment. All right, so let's do a very quick sketch of what we're dealing with. We're in quadrant 2, between two circles centered on the origin. Okay, so that's the region R we're dealing with. In general, if you look at the region that you're dealing with, your region R in this case, if it's some kind of circular thing, if it has something to do with a circle, or something to do with a paraboloid, or something that's circle-like, that's always a case where polar is better than Cartesian. If you're dealing with a rectangular kind of region, then you stick with rectangular. But if you ever see a circular kind of region, always consider transferring everything to polar and then do your integration. Okay, now let's describe the region R in polar coordinates. Okay, the region contains all the points R theta such that R is always bounded between 1 and 4, and theta is always bounded between pi over 2 and pi. Right? Pi over 2, pi, everything between the region that's distance 1 from the origin to 4. Okay? Next thing here is the function we're trying to integrate, cosine of x squared plus y squared. Now in polar coordinates, what would that look like? Cosine of r squared, right? Remember our 3 equations we need to know to do conversion. Going from Cartesian to polar, we use these 3 equations to do that. R squared is x squared plus y squared, which is what we got here. If they don't show up like that, then you just change x to r cosine theta, change y to r sine theta. So here it's very simple. We get cosine of r squared. Okay? Okay, so now what we're trying to do this becomes, first of all, cosine of r squared. dA, remember, is r dr d theta. All right, so that changes to dA turns into r dr d theta. Now the bounds here, notice that the way we've written here, r is going to be integrated first. So the r bounds here are 1 to 4, right? And then theta will be integrated last. And theta for us here is pi over 2 to pi. Okay? All right? So then we do the same thing we've done over and over again. We do the inside integration first. 1 to 4 cosine of r squared, r dr. So this happens first. D theta happens last. How would you integrate this? Substitution, yeah? With u equal to what? R squared, yeah. And du is 2r dr. All right? So that's the kind of thing actually you need to be pretty comfortable with, doing integration, substitution. So here, this will turn into 1 to 16. I'm also changing the bounds here as usual. And then this will be 1/2 cosine of u du. That happens first, and then d theta happens last. Again, you need to be comfortable with integrating things using substitution. Stuff like this should be very, very natural to you. If you're struggling with that, then you need to work on that. Then the rest of this is just very, very simple stuff. We have pi over 2 to pi, 1/2 sine of 16 minus sine of 1, quantity 1/2 sine of 16, 16 minus 1, yeah, sine of 1. Notice that there's no theta here. So this is just a big constant times theta when you integrate it. Okay, so at the end of the day, we get a difference of pi over 2 here in theta. So this becomes pi over 2 times 1/2. That gives me pi over 4 times the quantity of sine of 16 minus sine of 1. And there we go. Questions? Feel good about this? Yes? Let's do another one. Remember, the key is to remember dA is r dr d theta. And you got to change your function f into polar. And of course, you got to describe your region in polar also. Okay, this next one is going to be a little bit annoying because we're going to be using a few trig identities to integrate. But the setup is actually not difficult. Here, D is the region in first quadrant between x squared plus y squared is equal to 16 and x squared plus y squared is equal to 4y. This one is clear. This is a circle centered on the origin, radius of 4, right? This is clear. This guy here, this is a little bit less clear. So what you need to do here is to complete a square, which you know how to do, so I'm not going to spend time on doing that. And after you complete a square, this turns into x squared plus y minus 2, the quantity squared, is equal to 4. So this is a circle whose center is at 0, 2, and the radius is 2. Circle centered at the origin, radius 4. Circle centered at 0, 2, radius 2. So let's check out what's going on here. Big circle, radius 4. That's a beautiful circle, if I say so myself. Look at that. That's good stuff. Yeah. The other one centered on 0, 2. So center right here. Radius 2. So it's going to touch the circle right there and touches the origin. We only care about the part of that in quadrant 1. So we're talking about this thing right here. So this is our D. It's kind of like a claw shape kind of thing, right? Okay, just like last time, we need to describe that region D in polar coordinates, and those things will become our integration bounds. So let's do the easy one first. Theta is going to start from 0, right? We start accumulating that from 0, and we end the accumulation at pi over 2. That's what quadrant 1 is, 0 to pi over 2. What about R? How would you describe R in that region? Who wants to give that a shot? Yeah. Good. Yeah. Excellent. Very good, very good. So notice what happens when you accumulate these. This red line here, this is the distance that we need to accumulate. Notice that the distance starts from the smaller circle to the bigger circle. And therefore, that's going to tell you what R is going to be. We start from the smaller circle to the big circle. The big circle is R squared is equal to 16, or R is equal to 4, right? That's the big circle. The smaller circle in polar, left-hand side is R squared, right-hand side is 4r sine theta. Right? So this becomes r is equal to 4 sine theta. Big circle is r squared. R is equal to 4. Small circle is r squared is equal to 4r sine theta. Therefore, r is equal to 4 sine theta. So the accumulation of r starts from the inside, that's a small circle, 4 sine theta, and ends when we touch the outside, the big circle, r is equal to 4. Any question about that? Good with that? Yes? Let's see some heads nodding and shaking. Yes? Yes? No? Yes? Okay, good enough. Okay, now let's go to our integration. Remember, just like with Cartesian, the one with the constant bounds has to happen last. This one does not have, r doesn't have constant bounds. Theta has constant bounds. So theta has to integrate last. We have no choice. The last example, we actually had a choice because both of those were constant. We could have gone either order. Here we have no choice. We have to go r first, then theta. Y in Cartesian is r sine theta, right? And then dA is our r dr d theta. This is dA. This is y. All right? Let's keep going. 0 pi over 2. I have two r's here, so r squared. 4 sine theta, 4 r squared sine theta dr d theta. First round of integration is with respect to r. Sine theta is a constant, so we leave that alone. We're simply integrating r squared dr from 4 sine theta to 4. So the first round, initially at least, seems simple enough. Okay, so we integrated r, we get r cubed over 3, and r goes from 4 sine theta to 4. Sine theta is a constant as far as the first integration is concerned. Now let's keep going. I'm going to pull this 1/3 out of here, just to get it out of the way. Now, when I'm substituting r is equal to 4, I get 64. 64 sine theta minus, now this goes in for r, so that's 64 sine theta cubed times already 1 here. So that's 64 sine theta to the 4th power. Everybody see that? You see why it's sine to the 4th? Yes? Okay, any idea what to do from here? Okay, we can take out 64, sure. But that's the easy part, right? Okay, so what do we do next after the easy part? Yep, we got to use a trig identity here. So the identity that you will want to know are these two. And you might remember doing trig integration in 162 and 166. And you might remember back then that you had these often turn into something pretty messy just because they are trig functions and that's just the way they are. Right? There's a lot of trig identities that can help here and there. These are particularly helpful in a lot of things that you will see. Okay, so anyway, here we have sine to the fourth. We have sine squared. So this guy is this thing squared. So 64 over 3, 0 to pi over 2, sine of theta minus this thing here squared. Right? All right, keep going. Here we have sine theta minus 1 over 4, that's 1/2 squared, times the quantity of 1 minus 2 cosine of 2 theta plus cosine squared 2 theta d theta. And you use that identity one more time here for this squared. Cosine of theta is equal to this, so cosine squared of 2 theta is 1 plus cosine 4 theta over 2. Like I said, this is all we're doing is just playing with trig and all the annoying things that come with playing with trig. There's no way around it. You just gotta do it. So after doing that substitution again, we get this very annoying looking thing. So let me fill in the one step here. Okay, so I substituted this into here, and then there's a minus 1 over 4 multiplied by all of that stuff here. And once you got to this point, from here on, this is the easy part. We're just integrating very simple trig functions. Cosine 4 theta, you can integrate that. Cosine 2 theta, you can integrate that. Sine of 2 theta, all of that is easy to integrate. So after this is not hard anymore. And I'm going to skip all the annoying details there. They're annoying, but they're not difficult. So we get this thing. And that's really not the focus anyway. The focus is the setup and then using the identity twice to get to that point. Questions? Good. Okay, let's do one more here. Area of one petal of r is equal to sine 2 theta. You might remember when you took Calc 2, this kind of thing is, the shape is called a rose. When the coefficient of theta is even, there will be 2n petals. So this rose has 4 petals, and they're spaced evenly apart. Because it's a sine, it doesn't start on the axis. It starts over here. We have 4 petals of this thing. And they're, of course, the same shape. And the maximum radius, sine is always between -1 and 1, so the maximum r is equal to 1. Okay, we just want one petal. You can find any of these petals you want. Let's just find the one in the first quadrant, because it's the easiest quadrant to deal with. When you just want to find the area, you simply integrate 1 times dA. So your height function is just a 1, just a flat 1. So that will give you 1 dA. All right, so describe the region D. Let's do theta first. What's theta going to do? Where's it going to go? From where to where? That should be easy, right? First quadrant, 0 to pi over 2, yeah? And r, where's r going to start? 0, where is it going to end? Not always 1. It's 1 at a particular point, but in general, it's described by this. So sine of 2 theta. Okay? All right, so the area is going to be both of these. Well, let's see. This is constant bounded, so that's going to happen last. No choice. This one is not bounded by constant, so that one's going to go first. So we're going to have to go 0 to pi over 2. 0 to sine of 2 theta. And what's dA? RD theta, yep. And that's easy to integrate, right? Do you agree with that? That's easy to integrate. So I'm going to skip the integration here. It turns out to be pi over 8. There's no special trick needed, just r, right? R squared over 2, this thing here. You got to use that stupid, annoying identity one more time to integrate this to go to theta. But that's not hard to do. All right, let's do one more example. This time we're just going to set it up. We're not going to have time to carry out the calculation, but that's really not the point. We just want to set this up. Let's find the volume of the solid inside x squared plus y squared plus z squared is equal to 4. And outside the cylinder, x squared plus y squared is equal to 1. Okay, what shape is this? Sphere. So we have a sphere, and we're removing a cylinder from the sphere. So this is what happens when you take an apple and you remove the core, right? That's exactly what we got going on here. So let's see, we get here's my sphere, and we're removing a cylinder of radius 1 from inside that. So think of this as an apple with a core removed. It's really a cool gadget. You get this apple, you stick this. Anyway, it's a cool thing that it removes the core and gives you the apple, then you don't have to eat a core. We want to find the volume of this thing. So what we're going to do here, we can take advantage of symmetry. We're going to find the volume of the upper half. Then multiply by 2. We could have done the same thing with the petal, the one we just did. We could have found the area of half a petal in the first quadrant and multiply that by 2. There are a lot of chances where you could take advantage of the symmetry. Let's look at the top view, looking down from the top of this apple down onto the xy plane. When you look down, you're going to see the circle, the equator of that apple. Radius is 2, right? And then the core, the cylinder, radius is 1. And that shaded region here, this donut here, this is the D, region D we're talking about. And this seems pretty straightforward, right? Theta is from 0 to 2 pi. I'm going to go all the way around. And then R is bounded between 1 and 2. Seems pretty easy. Let's set up the integral here. Let's do theta last. If you don't know what order to go in, theta is always a very safe one to go last. Usually, there's a reason why dA is r d theta, because more often than not, you integrate r first and theta last. So in case of doubt, just go with theta last. It's easier to describe r as a function of theta versus theta as a function of r. So theta is always a safe thing to go last. And what do we want to integrate? What are we integrating? The height of this thing, right? Where do you get the height of that from? Sphere. Sphere says that z is 4 minus r squared under root, right? It's 4 minus x squared plus y squared. So that's 4 minus r squared. And the height above it, that's your z. And you take the positive root because we're taking the upper half. So this is 4 minus r squared. And then dA, r d theta. And let's not forget our 2, right? We're taking advantage of the symmetry. So we need a 2 here because we're looking for 2 halves of that thing. The integration is not hard, and I'm not going to address that, but getting from here to here, that's the main focus here. Okay, that's it. See you Wednesday.